Hello student, to the foundation of classical electrodynamics course. So today we will have lecture 8 where we are going to learn the differential calculus and start with gradient. What is the concept of gradient? Today we have class number 8. Okay. So, we will start a very new topic today, very important, and that is called the differential calculus. Okay. So, we know that if let f x is a function and this is a one variable function, right. One variable function. Now, if I want to find out what is the deviation of the function when we have a slight change in x, the dependent variable, then this is the way we write. A small change dx is there over the function, and then what is the change, that is my df. This is essentially f x. If I make a Taylor series expansion of this up to first order, then I have okay, and eventually these things will cancel out and I have this. So, what is df dx then? Del f, this quantity inside the bracket is basically the rate at which the function changes. So, that means this, if it is a single variable, I can remove this del and I can simply write ddf. So, this eventually tells us how rapidly the function varies. Right. So, df is the, what is df here? As I mentioned, the incremental and incremental change of f x and incremental change of f x due to the incremental change, rather I should say that simply that, because I do not know whether it is incremental change or not. So, rather I should, okay, let me erase this and I rewrite this, because the incremental, I do not know whether the function will change incrementally, because that is that the rate will going to tell me whether this function will change incrementally or not. So, I need to be careful enough to write this. So, rather I should say that, okay, I am writing here, I am not erasing this part properly. So, the this is for an incremental change of dx, because I am changing these dependent variables slightly. If x changes an amount, df. So, df is the change of the function due to the increment change of dx, that is all. Well, different kind of function we can have. Let us consider two different two-dimensional functions. In one case, these, say this is my f x and x. So, suppose the function is changing like this, and in other case the function is changing like this. So, this is x. So, in this case this is a slowly varying, this function varies slowly. So, this I can say this is a this function varies slowly. So, the slow variation, but in this case this function varies rapidly. So, this is a rapid variation. This is a rapid variation, this is a slow variation, this is a rapid variation, and that whether it is a slowly varying or rapidly varied function, that basically one can understand by calculating this term here. This rate of the change of the function can give us the idea whether the function is varying rapidly or slowly. So, with this note we can now extend the concept, and now the concept of gradient appear here. So, now we are going to understand what is the meaning of gradient. So, suppose this is a one dimensional two dimensional function or one variable function we are discussing, but let us consider a function t x varying with x y z. So, this is eventually this is a scalar function or scalar field. This is a scalar field. Now, this scalar field is a function of x y z. So, if I change x y z, it will going to change. Now, x y z can be defined by in the coordinate system can be defined by a position vector, and if the position vector changes, then how this t changes, that is the thing I want to write here. So, dt is a change of this scalar field when we have, say, slight change of r plus dr, and previously where it is r. So, in the coordinate system, if I try to understand, so in this coordinate system I am having here this point is r, and the function here I defined as function of r. This is the location I am talking about, not but this is overall t is a scalar field, mind it, this is a location, and here this is r plus dr, and t here the value is this. That is the thing just I wanted to mention. So, two different point, two different scalar values, but the change here is dt. Now, what is r here? It is a position vector. So, we know how to define a position vector, very first class we defined that. and what is dr? The increment or the length, small length element that we also defined in the previous class. So, r and dr are now defined. Well, now if I expand this dt for this 3-dimensional case, so how we define? In 1 dimension we know that I can define this df is del f del x dx. Now, f is a function of x, y, z. So, what should be the value of del f? It should add in this way with the other two variables. So, exactly that thing I will do here. So, dt, t is a function of x, y, z. So, I should write it as dx plus dt dy dy Now, this quantity I write in a nicer way, a very compact way, and that is the beauty here. So, please check it. I can write this quantity as a dot product of two vector dx I dot, because dx dy dz I know this is dr. So, I can write it as this way. So, if you make a dot product, you are going to get this. Now, I define this quantity, very important thing, whatever I get here, this quantity with a notation, and that is this dot, whatever we have here is simply dr. Okay. So, what is then this notation? This del, this is a operator and it operate over t. So, let me now rewrite once again. So, I am writing dt, the variation of t, as a operator operating over t. I am getting something dot dr vector here. So, this operator, if I now compare with this full expression, the operator should be this way. One can write this operator in this way. This is a very unique kind of operator. This is called the vector operator, associated with the partial derivative, but with a vector sign. Okay. This operator is called the del operator. The del operator or the gradient operator. Also, if I want to find out the gradient, what is gradient, I will discuss. Operator. So, you should remember that this is a partial derivative del x, del y, del z, and this del operator is associated with this expression, and this is expression, this is eventually at the end of the day is operator, and it will going to operate over a scalar field here, for example, like t. Now, if I want to integrate both the side, you can see that one interesting thing appears here. So, if I integrate here both the side, say dt with some initial point A to B, and in the right hand side if I look carefully, A to B, I am having two term here. One is this associated with operator and dot dr. So, eventually I am doing the line integral here. If you look carefully, this quantity, this is a quantity which leads to a vector field. This quantity at the end of the day leads to, because this is operating over t, t is a scalar, but this operator itself is a vector. So, this leads to a vector quantity or a vector field. And we know that when we have integration of vector field over dr and integrate with certain lines, it gives a simply a line integral. So, you should be very careful that whenever we have, so what is this operator then? T is a function of x y z, and then I have j y partial derivative and k z. So, this is the entire picture. T is a scalar field and I am operating this del operator over scalar field. What the outcome, what is I am getting is a vector field. So, T is a scalar field, but when I operate these things in this way with the del operator, I am getting a vector field. Now, what is this thing? This is a complete integral, right. So, close this. So, I can have this as, because this is a dt. So, I can have this as the result is T b minus T a. So, only the final points matter. I can have T is a scalar field, then I will operate over this del operator, I have vector field. Now, I am asking to I am asked to calculate what is the line integral, and I calculate the line integral. I find that this line integral, say point A to B, if I calculate this quantity, only depends on the initial value and final value. So, I can, from that I can also find a, so it does not, so what is the meaning of that? It does not depends on the path. Sorry, does not depend. So, it is a path independent integral you can have if you have something like this. Now, one very important conclusion we can make is that if I am having a closed line integral for this quantity, which is that this over t and then dot product of say dr, you will going to get this value, you will going to get 0. So, for closed line integral, if you find in the right hand side these quantity, so that has to be 0. Well, what is the general geometrical interpretation? So, that we quickly understand, and then maybe I will discuss more about and do some problem. So, geometrical so dt is equal to, I am having this quantity, right. Which is nothing but a dot product. So, I can write it as mod of this quantity and then mod of this quantity and cos theta of that. because the theta is the angle between dr and this quantity, whatever I figure out. So, theta is the angle between this vector quantity and dr. Okay. So, now for a fixed, if I for a fixed dr, so dr is fixed, you are in a point and you can go any direction you want, but dr is a fixed amount. The maximum change in t occurs because dt is the maximum, dt is the change. So, I want to find out what is how these things become maximum occurs when theta is equal to 0. That means, you can see that for theta equal to 0, what happened, cos theta will be 1, and then I am going to get dt maximum. So, for maximum, so try to understand this. This is a coordinate system and I am having a point here, this is r. Now, I can change my point in any direction I want, everything, so any direction I want. So, this is dr vector, but I am saying that for a fixed dr, that means all these directions are possible, but I want to change dr fixed direction, either this direction, I can move either this direction, I can move either this direction, either I can move either this direction. This is my choice, that I can move whatever the direction, but my dr mod of dr is fixed. Now, in that condition, you can see that if I move the dr in the direction along this quantity, so this is vector quantity, along this quantity if I move my dr, then that in that case it ensures that the change of dt is maximum. Okay. So, what is the meaning of that? So, the meaning is this quantity physically gives, this quantity physically gives the direction of the maximum change in the scalar field t. So, I am having a scalar field t which is a function of x, y, z, it is varying over the space. Now, I want to find out that at which distance this t is changing in a maximum way. So, if I calculate that quantity, this gradient of t, if I calculate, so that quantity eventually gives me that this is the direction along which the change is maximum. I can give a quick example here. Example means how to evaluate these things, and suppose t is given like a function, a scalar field is given like x square y z. This is a scalar field that is given. Okay. If this scalar field is given, I can find out So, how to find out this quantity? This is I del x, this is a short form. So, del x I am using as a short form of d dx plus j dy plus k dz, that will operate on t, and here okay, let me write it t, and this t is x square y z. So, I am operating eventually I del x plus j del y plus k del z, and this is x square y z. Fine. Now, if I figure out what is the result. So, first is the partial derivative with respect to x. So, the first term will be simply 2 x y z I unit vector plus y, this is x square z j plus x square y k. So, I am having a vector field. So, this is nothing but a vector field. So, whatever I am getting is a vector field here, right. So, at a given point this vector field, in a given point this vector field should have a value. So, if I want to find out okay, what is the value of this quantity at 1 1 1. So, I am now in a 1 1 1 point and try to find out that in 1 1 1 point what is the direction for which that the scalar field T is, the change of scalar field T is maximum. So, I already figured out this vector field, and now at 1 1 point I will just put the value. It will be simply 2 I plus j plus k. So, I am having a vector here, and if I find out the unit vector, so this is the direction, this is a vector. If I find only the if I only find the direction of this vector, that direction eventually gives me that okay, at this point 1 1 point, that is the direction along which the value of this T, that is the scalar field, is having a maximum change. Now, if I change my point to other, say 1 2 3 or 2 1 1 or 0 1 2, accordingly this direction will change, and this direction basically gives me that at that particular point, if I move to along this direction, then the change of the scalar field will be maximum. Okay, let us do more, because I have already a very useful expression here, that if I find the closed line integral of any given scalar field and then I make a gradient, and then if I want to find out the closed line integral, I am going to get a 0, that is a path independent integral I will get. So, if I want to find out the closed integral, it should be path independent. So, let us check whether we can get something like that or not. So, the problem, so okay, let me consider this as a problem. So, what is the problem? The problem says that, let us make it 2 dimension. So, I have a x coordinate, x y coordinate as Cartesian coordinate, and I am having a path like this. Last day we were doing a similar kind of problem. So, this coordinate point is say 1 0, no, this is say 2 0, and this point is 2 1. Okay. So, now I am going a path here from this path to this path, because I am going to calculate the path integral here, and another path is this one. So, this is my path 2, and this is my path 1. The problem is the scalar field is now given, the scalar field T is given, which is x y square. Now, the problem is find A to B, this point say A and this point B. A to B, what is the value of this quantity? What is the value of this quantity? So, this is how much that I need to figure out. Okay, so T is given, so I can find out what is the gradient of T. So, first thing first, so this is I del x plus j del y. I do not need to include k here because it is 2 dimensional, z is not there and it is operating over this. So, I can have I y square plus 2 of x y j. This is my vector field, and next thing is that I need to calculate the this quantity T dot dr. This is y square dx plus 2 x y dy, that is all. Now, I need to calculate this integral for 2 path. So, for path 1, integration so in path 1, so what we are getting, so first we need to check. So, this integration I need to calculate for say path 1, I just write it here path 1. So, path 1 is having two path, one is 0, it is from here to here, and when I am going from here to here, my dy is completely 0, only dx is changing, and when dx is changing, y value is 1. So, the first part of this path, it is simply 0, without doing anything I can simply say this value is 0. What about the next part? In the next path, when I go from this 2 0 point to 2 1 point, you can see that my x value is fixed, it is 2, but y is changing from 0 to 1. So, that means for this path my dx is not changing, dx is not changing. So, dx value is 0. So, y is changing. So, dy is non-zero and y is 2. So, I should have integration of 4 y dy, that is all, because x is 2, it is not changing. So, what value I am getting here? 4 y square by 2. So, integration 0 to 1, this is for the second part of this path, 0 to 1. So, eventually I am going to get 2. This is the result for path 1. What about path 2? I need to calculate the same thing, but for a different path, and this same quantity I am going to calculate. But in path 2, what we are getting? In path 2, you can see that I am directly going from this point to this point. So, there is a relationship with x and y, and the relationship is simply y is equal to so you can see the coordinate here. So, this coordinate is 2 1. So, simply y is equal to x divided by 2, that is the relationship between x and y. So, I just use this relation. So, here dy I can replace as half of dx, and then this quantity which I am having, I can already figure out this here. So, this is integration of y square dx plus 2 x y dy, everything is changing. So, now I am going to exploit this expression y. So, I can put everything in terms of either y or either x. So, let us put everything in x. If I do, y square is simply becoming x square divided by 4 dx, and then this quantity 2 x is there, y I replace like x divided by 2 and dy I replace half of dx. So, eventually I am having integration of x square by 4 dx plus 1 2 will going to cancel out. So, half of x square dx. So, 0 to 1, 0 to 1. So, eventually I will have x cube divided by 4 seems to be, and sorry, limit is not 0 to 1 because x is changing from 0 to 2. We have to be careful here. So, this limit is not 1, but 2 and 2. So, it is 0 to 2 and then half x cube by 3. So, here I am having, so x cube by 3 also. So, 3 multiplied by 4. So, 0 to 2. So, I should have 8 divided by 12 plus 8 divided by 6. So, it should be 12, 8 plus 16. So, it should be 24 divided by 12 and I will going to get the value 2. The interesting thing that is this 2 value, and here also I am getting 2. That means, what I am saying here is this quantity is a path independent integral. This is a path independent integral. This is path independent. That means, if I am having an integral in this particular form, then if you start from point A to this and then you, for example, you can go A to B in infinite way. You can choose whatever the path you like. There are infinite amount of way you can reach from A to B. We have taken two very simple path. One is path 1 and one is path 2. And you can see that for path 1 and path 2, both the cases you are getting the same result, and which is expected because this quantity has to be path independent. So, you will get the value 2 both the cases. If you now have a closed line integral, for example, if you start from A, then go to this point and then go to B and then come back A, you will get simply you will get 0, because in that case you have a minus 2 side here, and if you integrate the total thing, you should get a 0. Okay, so with this note I like to conclude. I do not have much time to discuss. So, today we will learn a very important thing, that the gradient of a function. If a scalar field is there, if you calculate the gradient, if you operate the gradient operator over the scalar field, this operator physically gives the direction along which the scalar field is increasing in a maximum way. So, the calculation is straightforward, and I believe you can also calculate, even if a scalar field is given, you can calculate the gradient, and you can find out what is the line integral also, if the line is defined properly. So, thank you very much for your attention. In the next class, we will discuss more about these problems, and we will see that how other things like divergence and curl emerges, two very important operators. So, thank you and see you in the next class.